Hello, welcome back. Okay, thank you for doing that. So it's good to see you all, good to hear you. Hello. So again, I have things to say. I always have things to say. I have ways I could go on, but I would rather not yet. What I would rather do, so this may be out of order, I'm not sure, but I would like to hear from you about what just happened in the breakout rooms. I mean, so two choices. Oh wait, are we recording? Yeah, okay. So, and this part will be recorded. Like the breakout rooms were not recorded for what it's worth. I mean, there was nothing to record. Ideally, if any of you right now has any questions at all that have arisen from your breakout room, like you were working on something and it's not resolved, or like, you disagree on something, or you're up to something and then I just interrupted you. Ideally, I would like to now publicly address any questions at all that came from the breakout rooms, sort of to warn you or to caution you. I mean, I think that would be ideal for you, and it could be in the private chat, or it could be public chat, or it could be with your voice, but I'd like to know of some concern or question that's arisen in a breakout room. If you don't have any, or if no one brings one up, then I'm going to start asking you questions. I know I sound mean. I don't know what's gotten into me. Sorry, it's a rough day. But like, I mean, I will start asking sort of more questions about what went on in the breakout rooms if someone doesn't come to the class's rescue and bring a question to my attention. So that's a polite, and then if it ends up being pulling teeth, then I'm just going to keep teaching. I mean, there are obviously a lot of things I can still need to say about this differential equation or about differential equations in general. But I think it would be more efficient if I hear from one of you about anything that is unresolved from any breakout room. So I will pause for a moment. Excuse me. I mean, I'm hoping that anything happened in the, like, obviously breakout rooms are dicey. We all know that. I'm kind of hoping, I want to pretend that something happened in the breakout room. Oh, here we go. Okay. Something in the chat. Oh, okay, wait, that's honest. All right, something's in the chat. And again, and by the way, guys, I mean, if I sound a little weird, like any admission of any lack of comprehension is more than okay. Like you should not be embarrassed about none of you should be, if there's something you don't understand or you got stuck, that's what I'm here for. I mean, I'd rather believe that someone was intellectually stuck than that just no one did anything or tried anything at all. So but okay, so there's something in the chat. Started doing this homework assignment. Approach letter B from part 1. Okay, hold on. So one person is saying that their group did try to help them, but that person is still lost. That's honest. That's helpful. I'm going to start looking up what they're talking about, and I may start talking about it. I'm just getting the sheet myself right now. But also, to be honest, I'd love to hear a little variety of what's going on. I mean, that's that. So I just heard about one of the groups, and I'm not going to mention names, but I think if I can get a little, and look, really, even if you just put in the direct chat, like, okay, in our group, like none of us had done anything and we talked about a football game. I mean, like, just tell me, I would love to know sort of honestly what happened in those rooms. Or if you tell me in my group, we had all done it already, we're bored, like, so we finished the whole thing and we've moved on to chemistry. Okay, but like, I would like to know what happened in those groups. And again, if what happened is that you're stuck, that should not be embarrassed. Oh, okay. Okay. Oh my God. Okay, I'm laughing. I'm not laughing at you. I'm laughing at how someone has changed their name. God knows how many times they've done that, and I didn't care. And it's totally fair. That's very funny that someone. Okay. Oh, interesting. Okay, so you guys are at different places with this. Okay, give me a little bit more. I mean, in the private chat, I'm learning things. This is good. I mean, but there's definitely a variety here. Like at least one group, their point seems to be that they're finished, which means I'm like wasting their time if I'm not careful. Another group, though, did finish the differential things and it's up to the vectors. That's cool. And I definitely need to teach the vectors, but then one person is confused. All right, give me like so I've heard from a few groups. I would love to hear like one more thing in the private or chat, but meanwhile, I'm opening the assignment. Hold on 1 second. And oh, wait, that's honest. Okay, now we're getting somewhere too. Like really, guys, I can help you so much better if you help me help you. And we all know that for some of you, I speak way too fast, but for some of you, I speak way too slow. I mean, for some of you, I say a lot of words, but you're like still waiting for me to say something informative. I know that. But the best way I can adjust to all of you is if more of you give me honest feedback on what to do. So no, and I'm getting that now in the chat. I'm seeing like some people need a bit about the chain rule and product rule and things like that. That's honest, and that wouldn't be the first time. And then some people need the vector stuff. Okay, and I'm not promising that I can help everybody right now at the same time. I mean, I can't do that, but at least if I know. All right, hold on. I'm just opening the thing. But I cannot emphasize enough that if there's still math things in your life that we're just now realizing were never straight before, that would not be news to me. And it would not be, one of the most exciting possibilities of my job is if ever I feel like I can get to be the guy that finally straightens out certain math things that that never did get straightened out before. I don't consider this too late to straighten out math things. I consider it exciting if I get to be the person that does that with you. So seriously, you're allowed to admit you don't know the chain rule or whatever. Okay, so I'm still looking at the chat. Okay, I'm getting more and more. I appreciate it. I also hope that it's clear that no matter who you are, no matter where you are, there's something in these sheets almost for I mean, at least the vector stuff is new to some people, I'm pretty sure. So there's something everywhere here for someone to, okay, I'm looking at the sheet. Okay, I'm about to make it, and I know we only have 21 minutes. It's fine. I'm about to make a decision of what, okay. And the vectors, yes, we're definitely going to deal with the vectors. And if all of you are up to vectors, great. But until like most of you are up to the vectors, I don't know that that's going to be my first priority today. So if you're up to the vectors, I take that as a statement that you're ahead of the game, that you're good, and that's good. And I'm going to ask you to be patient. If really the vectors are your only problem, that great. But yeah, probably not going to get to that today. But all right, I'm looking. Okay. Letter B from part 1. I'm just looking at letter B from part 1. Okay. I think if there's any, okay, I think I know what we're going to do. Okay. This is helpful. I appreciate it. Excuse me. Also, this is one of those days since I'm trying to, see where you're coming from. It's kind of like that. Again, that means I might really, really help. You might be one of the individuals that I really help today, and you might be an individual that gets nothing out of today from me. Like, I get that. And you might be totally tuning out, but I do want to warn you also, or just be fair, since I'm going to do something similar to this in the other section, but it'll end up being a completely different conversation. So I would encourage you, this may be one of those days where you want to check out both videotapes. I mean, both YouTubes. I may end up talking about something on purpose that's completely different in the other group, and it might be for longer. So just be aware that, that it might be worth finding out what I do in the other group. But okay. I'm sorry. I know I am stalling a little bit. All right. I think what I'm going to do here, I'm not going to talk about vectors right now. Again, this is all helpful to me to see where you are. Since the first person that said anything asked about, the first person that said anything in the chat was honest enough to ask about Roman numeral 1, part B, like toward the beginning, okay, to ask about a derivative thing. Now, again, I'm just trying to be as, and there goes my board. Hold on. Here's what I'm going to do. We've 18 minutes. Even if you're one of those people that flew through the whole sheet that really feels solid, I beg your indulgence. Stay tuned with me for a minute. I am going to go, what we are going to do is, sorry. Part 1, letter B. Okay, I'm going to address letter B of part 1 because I think one person had the guts to say they wanted help with that. I feel like that person is probably not alone. I think it does take guts to say that. I think there are other people in the room that could use a little clarity on the heart of this whole issue, which is this question. 1B, the question where it says, is x equals a cosine omega t, is that expression a solution or not? To this differential equation. So this is a question that someone asked about right now. Some of you may be clear on this already, but I think that some of you might not be. What I'm going to try to do right now when I refresh this for 16 minutes, I'm going to try to address all of you. Like the answer to this question does involve the chain rule, right? Which a couple other people in the chat asked about. And I'm going to say to all of you, some of you may be very clear on the operation of the chain rule at this point, but I'm going to show you a little piece of notation that might actually enhance your perspective on the chain rule, even if you think you already know how to do it. I want to show you something that might be a little bit new to, so I think it's worth it to everybody, hopefully. And yes, this question here is the heart of the matter. The heart of the matter is, given a certain differential equation, is a certain expression a solution or not? We are trying to solve, so we're trying to solve differential equations. When we say we're trying to solve the differential equation, just to remind you, we are going backwards. It is reverse engineering. The differential equation says that there is a certain x in the world. There's a certain x, which is a function of t, such that when that x is differentiated twice with respect to t, it yields back itself times this thing called omega squared times -1. Like, and no, hold on. Let me back up for a second. First of all, omega squared. We didn't talk about omega yet in lecture. I know you've talked about it in lab, blah, 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 blah. We didn't talk about omega, let alone omega squared in lecture. It is the next lecture thing to emphasize. But let me say, right, so it might be intimidating to some of you. Omega is a Greek letter. It's a lower, I mean, that thing that looks like a W, excuse me. The thing that looks like a W is the Greek lowercase letter omega. It is a Greek letter, but it's just a letter. It is a letter that stands for a constant number. It has meaning. It has implications. It has power that we're going to get to. But as far as the math is concerned, all we need to know about it is that it's not a variable. Omega stands for just some number that doesn't change throughout the problem. And therefore, omega squared stands for some number that doesn't change throughout the problem, throughout the differential equation. So let me say that one more time. Omega squared is one package right now, as far as I'm concerned. Excuse me. Omega squared is just a number. It might as well be called beta or K over M or square root. Like, it's just a number. And the fact that it's squared, you'll ultimately see why we squared it. But for the moment, it doesn't matter. We could have cubed it. We could have quadruplified it. We could have quartered it. And it's just literally a number. So what the differential equation says is that there's some X function in the world, which when we take two time derivatives of it, yields back X itself, like produces itself again, times some number times -1. Right? So we're looking for an X that does that, right? Like, if we're trying to solve this differential equation, we're looking for an X function of T that meets that condition, that works. I say works means is consistent with that equation. Then that's if we're literally trying to solve it. And literally trying to solve it means looking for an X expression, which again, is unusual. It's already confusing to some of you for good reason, because what you're used to thinking is that the answer to a physics question is to be found by plugging into some X formula, right? But here, what we're looking for is the formula, if you like, okay? That's number one. But now, on top of that, I have not told any of you how we come up really directly with a possible solution to a differential equation. It is, in fact, reverse engineering. It is something that has to be sort of guessed in an educated way or induced from experience. I have not given you a method for coming up with a solution to a differential equation. But what I have told you is that once you have a possible solution to a differential equation, once you have an educated guess on the table, then you have an ironclad method for checking, for verifying whether the guess is in fact right or wrong. And the ironclad way of guessing or testing whether a certain guess is right or wrong is by differentiating, by taking derivatives. Now, so what's happening in the homework here, it is confusing, honestly, like really. And by the way, if there are people in the room that really are on top of this now, and if you're one of the people that doesn't get this yet, don't be ashamed, and please keep listening for the next couple of days. But also, if in your heart you're slightly intimidated by some of the people in the room that maybe already do seem like they get this, can I please tell you that at least some of those people that right now seem to get this because they came to me with questions and confusions a couple of weeks ago about it. And I'm saying this as a compliment to everybody. I'm not saying that as an insult, but I just want to be clear that all of us have to go through a process where our brain bumps over this differential equation stuff. And some of the people in the room, I just know for a fact, asked me really good questions about it like a few weeks ago, and they got themselves over the bump or the hump, and they should congratulate themselves for that. But don't think that they didn't have to ask questions too. Again, that's a delicate thing for me to say, but I'm saying it as a compliment to all of you. There's something bumpy and weird about this because the homework now says, given blah, it says given is blah, a solution to blah. Like, that's so backwards and weird to all of us. But it's saying is x equals a cosine omega t. If I'm looking at B now, it's saying, does that work? Does that satisfy? Assume we're guessing that as a solution. Now it's true or false. Is it true that that's a correct solution? Or is it false that that's a correct solution to the differential equation? So how do we find out? We take derivatives. Okay, that's what I'm going to do now with 8 minutes left. like the function that we're testing, what we're testing is x equals a cosine omega t. Now, the way we have to take, so we're going to take derivatives. We're going to take a derivative and then a derivative again. The way we have to take derivatives is twofold. Number one, we have to know our trigonometric derivatives. We have to know that the derivative of, well, okay. Oh, so sorry. So in order to take, and I am watching the clock. Well, to take derivatives, okay, number one, note, if y equals if y equals sine of x, then this is just in general. Now, this is like a GDP I'm saying here. Step 3. Like if y in general equals the sine of x, then dy dx equals cosine of x. Like in general, the derivative of sine is cosine. If y equals cosine of x, then the derivative of y with respect to x equals negative sine of x. Now, I'll also tell you that someone was in my office yesterday asking really good questions about this fact that I just wrote down. Now, I'm watching the clock. So I know that many of you just know this as a fact from math, like the derivative of sine is cosine, the derivative of cosine is negative sine. And if you've memorized it, that's good and it's correct and it's powerful and we need it. But I'm really pleased that at least one person came into my office and literally sat down and said, I know this, but like, I totally don't get why. Like, it seems weird to me. Like, first of all, why is the derivative of sine cosine? Like, that seems like a weird coincidence. And second of all, even when the person was saying, like, even if I get that, like, why is the derivative of cosine negative sine? Like, where'd that negative sign come from? Such a fair question. And we sat down and looked at pictures and looked at graphs and we showed it to each other why that is. And honestly, if I didn't have only 5 minutes left in the class today, I would do that right now, because especially those of you who think there's no issue and have just memorized it and are comfortable with it, shame on you maybe. Like, don't just memorize it. You honestly do want to unpack and think about why would the derivative of sine be cosine? And if I even understand that, why, when I go the other way, is there a negative sign introduced? The answer is look at the graphs and look at slopes. I mean, that's the simple answer. Like, a derivative means a slope. But like, look at them. It's actually fascinating that this is true. But you can show yourself that it's true if you look at a sine graph and look at what the slopes of it are doing as you track the values of it. Okay, so that's number one. But we do need to know that one way or the other. And remind me next class, be honest, if you want me to show all of you in pictures, it's worth it. But that's number one, so that the derivative of sine is cosine, the derivative of cosine is negative sine. But then number two, with 5 minutes left, comes the chain rule. The chain rule. That's an independent idea that we also need when we're doing this derivative, because this derivative is complicated. It's not just a cosine, but it's a cosine of a function, right? It's not the cosine of x or the cosine of t. It's the cosine of omega times t. That's a function itself. So what is the chain rule? I know many of you know it, but have you ever thought to write it this way? Here's the chain rule. If y is some function of x, right? And if z is some function of y, right? If we have a function of a function, then what the chain rule says is, well, then the derivative of the entire thing, so to speak, the derivative of z with respect to x, right? The derivative of the dependent variable with respect to the ultimately independent variable is, think about it this way. It's just this. Like, whoa. Like, if you really, I don't mean that sarcastically, and I know I have 4 minutes left, but look, if nothing else, to those of you who already think you know, who already do know the chain rule, this is just another public service announcement or another example of how this freaking notation means something. The notation works. What I just wrote here is that the derivative of the outer with respect to the inner, like the derivative of the whole thing equals the derivative of the outer times the derivative of the inner, because the dy's just cancel. So you get dz over dx. Like, if you follow notation at all, it actually makes, what does this mean in practice? As a concrete example, it means, in this case, like, let y equal omega t. Let X equal a cosine of Y, right? Like a function of a function. Then dy dt, the derivative of the first function is omega from power rule, so to speak, and dx dy equals negative a sine y. Thus, dx dt equals negative a, well, negative a sine of y all times omega. In other words, negative a omega sine of omega t. Right? That, okay, we have 2 minutes. I did that a little bit fast, but I'm trying to say you do the derivative of the inner, which is omega, and you multiply that by the derivative of the whole outer, which is negative a omega sine omega t. So we get negative a, I'll say that again more slowly on Wednesday, but that's the chain rule. So of course, that's the one thing the person wanted to see, and I just did it really fast. I know that. I'll do it slower, but I am watching the clock. But that's the derivative of that's the first derivative. Then if that's the first derivative, we have 2 more minutes. That's the first derivative. I'm just saying you got to multiply the whole answer by omega, because omega is the derivative of the inside. But then we'd have to take the derivative again. The derivative again is negative a omega squared cosine omega t, which is the same thing as negative omega squared a cosine omega t. I am going a little fast right now. I do recognize that. That's the second derivative. Why am I taking 2 derivatives? Because the whole differential equation that I'm testing says that the second derivative is supposed to equal negative omega squared times x. Well, look, the second derivative equals negative omega squared times a cosine omega t, and a cosine omega t is x, supposedly. So this one works. I mean, again, I went a little fast. Okay, I'll stop saying that. But look at the notes. Back up. Just what I'm saying is we took 2 derivatives to find out whether, when we took 2 derivatives, did we get back the original thing times omega squared times a negative sign. I don't care what omega squared means. It's just a number. But it turns out that that function, if you choose that function for x, then yes, when we take 2 derivatives of it, we get back itself times omega squared times a negative sign. So the answer is yes, it is a solution. You all have been very, very patient, very thorough. We'll keep going over this. Keep giving me the feedback. It's super helpful. You're all good people, and you're all going to get dual degrees. Okay. But I'll hang out for questions. But thank you. I'm good if you're good.
Have a good day, Professor.
Oh, thank you. You too.
Have a great day, Professor.
Thank you, guys. Oh, wait, someone just said something. Thank you, guys. And if you have a question, you hang up. Thank you. Ash. Wait, thank you. Wait, someone just said something in the chat. Oh, good. Oh, great. Thank you, John. Okay. Stephen, yeah. Oh my God. Okay. Those names are very funny. Very funny. Okay. Shakia, you okay? You have, oh, I'll stop the recording. Hold on, I'm stopping the recording.